Hello everyone, welcome once again to Nated Engineering. Today we are still on friction engineering science entry, and this is the second video. I want us today to talk about a body that is resting or that is at an inclined plane. Obviously, you can't talk about an incline without having an angle of incline. So this incline is having an angle of theta, and we're going to have a body of mass m. One thing we have to know about gravitational acceleration is that it is always acting vertically downward, irregardless of whether we are dealing with an inclined plane or whatever which is not parallel or which will not be perpendicular to the gravitational acceleration. That is telling us that the weight of this block is going to be like this: mg. We know weight is equals to mass times gravitational acceleration. And we said that when we are having a force, because mg is a force, it's weight and weight is a force, it's given in newtons. We said when we are having a force that is acting at an angle, that force will develop two components, which will be the component that is perpendicular to the surface plane that we are working with, and the component that is parallel to the surface plane that we are working with. This angle is equals to theta. This angle, this theta, and this theta, they are the same thing, this angle and this angle. So using trig ratios, we are going to have something like this. This being the weight, that's something else. This being the weight, mg, and the force that is perpendicular being this one, and then we're going to have the force that is parallel. It will be something like this. This we said will be our theta. We are going to use trig ratios, which is SOHCAHTOA. Our SOH is this is sine theta, which will allow us to use the opposite over hypotenuse. The opposite will be this one. The opposite will be this one, and the hypotenuse will be this one. The hypotenuse we already have as mg. So what we are going to do is we are going to say sine theta is equals to the opposite, which is this one, divided by the hypotenuse, which we know by now that is mg. So for us to be able to get the opposite, the formula that we have to use is mg sine theta, meaning the value of this force will be represented by this formula, and it is what? It is parallel rather to the surface plane that we're working with, meaning it is pushing the block to be going down. It is pushing the block down, or it is trying to push the block down the slope. That is why I put the force here. That will be our mg sine theta. The value of this force will be represented by this equation, and the value of this force, we are going to use cos for it. It will be cos theta. We know cos is what? It's adjacent over hypotenuse. Adjacent hypotenuse. What is our adjacent here? Is this which we are looking for. Our adjacent is divided by what? Hypotenuse, which we know by now that is mg. Meaning our adjacent, if we make it the subject of the formula, we're going to get mg cos, this is cos theta. Meaning the formula that represents the force that is associated with this line, or the force for this the force at this line, this force will be mg cos theta. These two forces are always there. Before we can have an external force that is applied, maybe a force applied saying it is trying to pull the block, let's say, up the slope or down the slope, these forces are always there. And remember, this force is acting what? Perpendicular to the block. We can tell that the block is not moving in that direction, nor is it moving in that direction. What does that tell us? It says that there is a force here that is balancing this force, and we know that it's called what? A normal reaction. Normal reaction is always perpendicular to the surface plane that we are working with. These three forces, before we have a force, an external force that is applied to this system or to the block, these three forces will always be there. They never change direction. So let's add a force. I just want to redraw because I think it's not visible, clearly visible. We're having what? The block here of mass m. There will be a force perpendicular to the surface plane we're working with, and it is mg cos theta. We know by now. We are having a force in that direction, which is what? Mg sine, it's mg sine theta. And we're going to have normal direction. Now, what do? We apply a force which is trying to pull the block up the slope, or is pulling the block up the slope. Let's give it F, say it's force F. Automatically we know that there will be a force which is frictional force opposing motion. We know frictional force always oppose motion. We do not put the direction of frictional force before we know the direction of motion. If we do not know the direction of motion, that simply means we do not know the direction of frictional force, because we know that frictional force always opposes motion. So what's going to happen here is that we have to equate, first starting with the forces that are parallel rather, to the surface plane that we're working with. In this case, it will be the forces that are going up the slope, which is F. We can see that it's only F, are equals to the forces that are going down the slope. These two are going to the same direction. Therefore, they will be on the same side of the equal sign, and we add them. It's mg. We add them because they are working together. Sine theta plus frictional force. And then we also have to equate the forces that are perpendicular, which will be normal reaction is equals to mg cos theta. Cos theta. This is theta. Remember, you don't have to cram these formulas. As long as you draw the correct structure and then you say forces going up the slope are equals to forces going down the slope, because this is not a standard equation. It can change. For instance, if we were to say, now this is the force applied. It's force, they apply the force going downward, it will be force down. This will then be our frictional force. Why? Because it opposes motion. And this formula is now going to change. It's no longer F is equals to mg sine theta plus frictional force. It's then going to say, let's look. The forces going up the slope, it's frictional force alone, are equals to the forces going down the slope, which is mg sine theta plus the force that is applied going downward, force down. So you do not have to cram these formulas. You just have to know how to draw the correct diagram from what is described to you and then take it from there. Equate the forces going up the slope to the forces that are going down the slope. So let's add something. We are having a slope again. This is theta. This is our block of mass m. By now we know that there will be this force, which is normal reaction. We are going to have this force, and we are going to have again this force with mg cos theta. We are going to have this force again, which is mg sine theta. And now, depending on the direction of motion, we are going to have frictional force in the opposite direction. So let's say now the force that we are dealing with is now applied at an angle. Let's say it is at an angle. It's pulling the block up the slope, but it is pulling at an angle of alpha. What is the one thing that we know about a force that is applied at an angle? It will develop two components, meaning we are going to have a component that is parallel and a component that is perpendicular to the slope that we are dealing with. This, let's say it's F, force F. Using trig ratios, this we are going to get as F cos alpha, not theta. And then this we are going to get as F cosine alpha. We do not use this force because from it we already got the value that is responsible for the vertical component, the vertical impact, and the value that is responsible for the we have the value that is responsible for the impact to the block that is parallel to the plane, and we also have the value that is responsible for the impact on the block that is perpendicular to the block, meaning our frictional force will be on the opposite direction because the block is moving up the slope. Therefore, that's why I say we do not cram equations. From here, you have to equate what you see before you. So we are going to start with the forces that are parallel. We are going to say only F cos theta is going up the slope if you look at the diagram. Therefore, it will be F cos alpha F cos alpha is equals to, these two are going to the same direction. They are on the same side of the equal sign because they are working together. It's mg sine theta plus the frictional force. Now let's equate the forces that are acting perpendicular to the plane that we're working with. We're going to have normal reaction. It's going up with what? With the force which is F sine alpha. It's equals to F cos alpha. By now, we know how to get the direction of the two components. If you do not know, that means you haven't watched the series of videos on forces, which is the topic forces. And if you haven't done that, please go and watch forces so that you know how to you know more about these forces, how to get the directions, and yeah, it will explain more of that. We explain more of that in forces. So this is how the equations that we are going to use now when we are dealing with a diagram like this. We can change the diagram again. Let's say maybe, let's erase this. Now I want us to play around with the force. Let's change the force and see how our equation is going to change. We have a slope of angle theta, again mass m, and we know by now that we are going to have these forces: normal reaction mg cos theta and mg sin theta. So remember on our previous diagram, we had the force being applied. We had the force applied like this. Now let's change the direction of the force to something like this. We know if a force is applied at an angle of alpha, it will develop two components, and those components will be like this. Because the force is going in that direction, the components are also going towards this point. Unlike on the previous diagram, they were going, because the force was going in that direction, they were also going in that direction. The force has changed, now the components must also change. The force, let's say it's a force of F. We are going to have F cos alpha. Let me move this down. We are also going to have F sin alpha. And then, because the force is applied, the force applied will cause the motion to be in that direction. We are then going to have the frictional force in that direction. And then from here, we equate. We'll start with the forces that are parallel to the surface plane, which will be, starting with, we are going to have to say the forces going up the slope are equals to the forces going down the slope. The only force that is going up the slope we can tell that is F, as the frictional force. This F cos alpha and mg sin theta, they are going down, meaning they will be on the same side of the equal sign, equals to this, and it's mg sin theta plus F cos alpha. Look at the forces that are perpendicular. Normal reaction is going up. The F sin theta, sin alpha is not going up, therefore it's equals to F sin alpha is on the same side of the equal sign with mg cos theta, because they are going down on the same direction, mg cos theta. So these are the equations that we are going to have for this scenario, and they are unique to this scenario. That is the reason I'm saying do not cram. Know how to get the directions of the components. Know how to draw from what is described to you. Formulas that you have to know. Theta is equals to mu, which is the coefficient of friction, and frictional force is equals to the coefficient of friction times normal reaction. These are some of the formulas that you have to cram, if not the only two. If you know how to equate, you are fine. And then from here we will do an exercise on the next video to see how exactly a question asked on this topic and how do we go about solving them. I will see you on the next video.